A few days ago, I was scrolling through the Wikipedia article for double factorials, as one usually does, and while looking at the Additional Identities tab, I came across something that caught my eye. The double factorial of 2n over the double factorial of 2n minus 1 approaches the square root of pi times n. Hello, it's me, and this is double factorials and pi. Pi is notorious for showing up in everyone's business, and it's no surprise that we found it here. But before we get ahead of ourselves, we're going to need to backtrack. The factorial of a positive integer n is the total product of all the numbers less than or equal to it. It is often denoted as n with an exclamation mark beside it. Factorials aren't really going to be the matter today. We're instead going to look at double factorials. The double factorial of any number will be almost the same as a factorial, but we're only going to take the numbers of the same parity, even or odd. We could express this in the following way. Now, I admit this does look like a lot, but we can break it down easily. This expression basically means that for our number n, while k starts at 0 and increases by 1 in every iteration, we're going to multiply by n minus 2k n over 2 minus 1 times. It is quite the mouthful, so it's probably better that we just represent it like this. Notice how, depending on the parity of the number, we either get 1 or 2 as our final value. This whole expression will be necessary later on, so let's just keep it in mind for now. Now that we understand the concept of a double factorial, we can plot the ratio from the beginning in decimals. That fluctuating orange line is that division from before, and the smooth green line belongs to the square root of pi n. With all of this in mind, we can now move on to our next resource that we will use for our proof, the integrals of Wallis. The Wallis integrals are a family of integrals that were introduced by John Wallis, a mathematician from the 1600s, known for being one of the first to utilize the infinity symbol and pioneer the concept of infinitesimal calculus. These integrals we will be using shall be represented as w of n, where n is less than or equal to 0, and are defined by the integral from 0 to pi over 2 of sine x to the power of n in terms of x. They are often used in calculus as a form of problem solving due to us being able to swap out sine for cosine and obtain the same result. This is because both functions are mirrored in this bound. Cosine decreases at the same rate from 1 to 0 in the interval of 0 to pi over 2 as sine does. With this knowledge, we can try to solve this integral through integration by parts. This lands us on the following result. W of n is equal to n minus 1 over n times w of n minus 2. Pay close attention to that duplicated w term. Since our integral w is inside the result, we can call it a recursive function, which means we can write this in the following way. But wait a second, does this not remind you of something? Let's bring in the expression of double factorials from before. Look at how similar they are. Does this mean that we can represent our integral with double factorials? Well, you'd be correct. We can expand this big pi expression, and we're going to get a very similar pattern to before. We can use double factorials to write the top and bottom terms. But let's not forget about something. Depending on n's parity, we're going to get one of the two different values, w of 0, which is pi over 2, and w of 1, which is just 1. This looks very similar to our ratio from before. Just substitute n for 2n and shove our pi over to the other side, and we have the same expression. With all of this in our system, we can finally move on to the last chapter. Limits. Limits are a funny thing. They sort of contradict our regular line of thinking. To show an example, let's take a relatively large number, say 1 million, and divide it by the consecutive number, 1,000,001. You're most definitely not going to get 1 as a result, and the more we increase that number, the closer our result gets to 1. So we can say that, as n tends to infinity, n over n plus 1 will be equal to 1. Wait, but does this imply that n is equal to n plus 1? Well, no, it never will be, but in the terms of limits, it will. Before we get too far in playing with infinity, let's utilize this for our integral from before and say that w of n will be equal to w of n plus 1 as n tends to infinity. Now, let's move these two equivalences aside, as they will be a little more important later. Expanding our integral from before, and assuming n is even, we're going to get the following equation. And if we do the same for w of n plus 1, if you haven't noticed yet, a lot of these terms are the same, which means that we can cancel them. In fact, if we multiply w of n by w of n plus 1, we can get rid of all terms except for 1 over n plus 1 and pi over 2. And moving the n plus 1 to the other side, it gives us this neat equation. Now we can utilize our equivalences from before, where n approaches n plus 1 and w of n approaches w of n plus 1, and we can substitute them into our result, which gives us this, which we can solve to get w of n equals square root of pi over 2n as n tends to infinity. This is the last step to get to our final result. The only thing we have to do now is replace n with 2n. As previously seen, we can represent w of n with double factorials like this. Solving this equation will finally result in our identity from before, square root of pi n. Thank you so much for watching this far into the video. Please consider liking, and depending on how well this goes, I will see if I can make more stuff like this, since it was very fun. Hope to see you soon, and goodbye.